Oh, my mom knew that I didn't do anything.
All right, if you guys can turn to page 7, let's do a little bit more solving trig equations. And then we'll move on to derivatives. Okay, so page 7.
Is this next test going to be as hard as the last test?
It's a lot.
Oh, man. God.
Okay.
He said it's a lot.
I mean, it's everything we've done.
So looking at 34, I just want to kind of recap. So recapping, 2 cosine squared minus cosine theta. If we bring everything over to one side, set equal to 0. We can think of this as an easier problem to factor. If we bring everything in terms of x, if you find that helpful, factor in terms of x, bring it back in terms of cosine, and then look for the solutions individually. So cosine of x equals to 1 when theta equals 1. Cosine of theta equals -1/2 in the second and third quadrant. Okay, let's look at number 36 and 37. So 36, if you think of it in terms of, oh, where is sine equal to cosine? If you know you're in a circle, you can think of it that way. Well, power 4 is when sine and cosine have the same values. But we can also do this algebraically. I want to show that to you. Normally, I would say that we don't want to be dividing by a trig function, because when we do that, we don't want it to disappear and cancel out. But in this case, if we divide by cosine, we're just changing it into a different form. So we're not losing anything when we do this. Okay, so I want to see what happens when we divide by cosine. Okay, so what's sine over cosine? Tangent. Sorry, I want to record this. Okay, tangent of theta is equal to, what's cosine over cosine? 1. So I think it's a lot easier to see that relationship. Where is tangent equal to 1? Think about your unit circle here, right? Tangent is equal to 1 when the x and y's are the same. Sine over x, or y over x, sine x over cosine x is tangent. Okay. Where else is tangent positive? Because we know that there are 2 locations where tangent is equal to 1. Yeah, third quadrant. You know it's going to be a variation of pi over 4, so we want a fractional value that's greater than 1 but less than 1.5, so that's going to be 5/4. Okay, before we move on to 37, I want to do a little bit of review from the handout I didn't get a chance to give you yesterday. This is the trig review handout. Hopefully you guys picked this up just now. First of all, almost all the problems that we're dealing with is going to be in terms of radians. There's very little degrees that we have to worry about, or conversion in terms of degrees. There's a few, but the majority is radians. We have to know SOHCAHTOA. We have to know the relationship between the inverse functions. Sine and cosecant are inverses. Cosine and secant are inverses. Tangent and cotangent are inverses. But then tangent and cotangent can also be written in terms of sine and cosine. So that, hopefully, we all know pretty well. Identities, okay? We do need to know these identities, but I will say that the ones that are highlighted are really the only ones you need to memorize, and the other ones you just have to just know how to derive them, and I'll talk about how to derive it. The one that we recognize hopefully the most is sine squared plus cosine squared equals 1. There's 2 more variations of Pythagorean identity, but those we can just rely on this little trick here. If I divide everything by sine squared, we can arrive at this identity. So let me show that to you. If I have sine squared plus cosine squared equals 1. If I divide everything by sine squared, one of the known identities is going to just pop up if we know our reciprocal identities. Okay, so sine over sine is 1. Cosine over sine is cotangent. And then 1 over sine is cosecant. There, right? There's no need to memorize it. You just do a little bit of rearranging or deriving, and you can arrive at one of the other identities. Right? Okay, here's the other one. If I have sine squared plus cosine squared equals 1, divide everything by cosine squared. Sine over cosine is cosine over cosine is, and 1 over cosine is right. No need to memorize these, right? If you know one of them, you can arrive at these other two. Okay, sine and 2 theta, we need to know that. Sine and 2 theta can be expanded into 2 sine, cosine. Cosine of 2 theta, if we just know this one, cosine squared minus sine squared, then these other two we can just arrive at just by replacing one trig function with the other. So this is what I mean by that. Let's say we only knew cosine squared minus sine squared, which is fine. If I can get everything in terms of sine or everything in terms of cosine, then one of the other identity possibilities begin to show up. So if I start off with cosine squared minus sine squared, I can replace cosine squared in terms of sine, right? Because we know that sine squared plus cosine squared equals 1. So cosine squared equals what? 1 minus sine squared, right? Just rearranging this equation here. Cosine squared equals 1 minus sine squared. If I make that substitution, 1 minus sine squared, combine like terms, I get 1 minus 2 sine squared. Vice versa, if I were to take that sine squared and find a substitution for that, I know that sine squared is equal to 1 minus cosine squared. Once I make that substitution, careful, there's a negative outside that I need to distribute. So I get negative 1 plus cosine squared. So I'm left with cosine squared plus cosine squared equals 2 cosine squared. So there's our other double angle expansion possibility. Unit circle, it's good for you to review through the unit circle on the back page of this handout. I have a blank and a filled out version. So if you want to practice filling it out just to kind of help remind yourself the radian measures as well as the order pairs. Okay. Even in odd functions, sine is an odd function. That just means that if I see a negative inside of theta, I can just drag that out in front as a coefficient. Cosine is an even function, which means that any negative inside the angle just disappears. Okay, so cosine disappears, but the sine gets dragged out in front. Don't have to worry too much about this, just the cofunction relationship between sine and cosine. Unit circle values, and don't worry about too much about the graphs. Transformation is not a topic that shows up on the AP exam, so we can ignore the graph portion. Okay, so back to 37. Cosine squared plus sine theta equals 1. We have a much easier time solving an equation if we can get everything in terms of one trig function. So which one is easier to work with and change? The sine theta or the cosine squared? Yeah, the cosine squared, right? We have that Pythagorean identity. I could just get that in terms of sine and just work from that perspective. So I'll change cosine squared. Cosine squared equals what? Yeah, 1 minus sine squared. Rearrange, right? I'm going to just bring everything over to one side and see if I can combine some like terms. Right? The ones can cancel out. I'm just left with two terms. I can just look for GCF. I'll put the positive term first. Okay, what can I do from here? GCF. Factoring out means dividing it out. Sine over sine becomes minus sine theta. Where did the division? Oh, you mean over here?
No, like it's cosine squared theta divided by sine.
That's a plus sign.
Oh, sorry, that's a plus sign. Yeah, it's not very clear. Okay, so sine theta times 1 minus sine theta equals 0. We set both portions equal to 0. Okay, rearrange this as sine theta equals 1. Okay, so where's sine equal to 0? Yeah. Sine is the y value, right? 0 and pi. Okay, where's sine equal to 1? Y value. Okay, there's more solving trig equations that we want to do, but we'll come back to it. Okay, let's shift our focus over to trig derivatives, and then we can revisit solving equations a bit more when we come back to it after when we get closer to test review. Okay, any questions so far? Okay, let's go to page 9. We'll start our discussion on trig derivatives. So most of the semester, we're able to get through relying on just one derivative rule, right? We did power rule for the longest time. That was the only one that we did up until this last unit, right? This last unit was when we started involving more rules: natural log, e to the u, log base a to the u. So we now have another set of derivative rules, and these are trig derivatives. Okay, we have 6 of them. It's a lot, but I'm hoping that I can kind of present it in a way where there are some nice patterns that we can put into the table, and hopefully the more patterns that you can see, similarities, combinations, or patterns that you can see, the easier it is, I think it is, to memorize it. And then the week after break, we also have to learn about derivatives of trig inverse functions. So those are another set. Those ones look the most complicated. So so that will end the derivative rules and end this semester. Next semester, I know it's daunting. We got to learn all these anti-derivative rules on top of these derivative rules. But the good thing is the integral rules are basically just working backwards from these derivative rules. So if you know the derivative rules, then just understand that you're kind of working backwards. There's some slight adjustment, but working backwards. So that kind of makes it a little bit more manageable understanding. We're just kind of working with the same set of rules. We just have to kind of undo the derivative rules next semester. So I want to think of the sine and cosine derivatives as kind of like the parent functions. We have 6 of them, right? There's a rule for tangent, there's a rule for cotangent, there's a derivative rule for secant, there's a derivative rule for cosecant. But right now, let's just think of sine and cosine as kind of like these parent derivative rules. And we can actually arrive or derive these other derivative rules simply by relying on sine and cosine. We're not going to do all of them. Let's just do one of them, and then we'll just shift our focus to helping us work towards memorizing these rules, giving you a structure to help you memorize it a little bit easier. And then we're going to work through derivative rules on the back page. Okay, so we know the derivative rule for tangent is secant squared, but we're going to try to just rely on these two to help us get there. Okay, so how can we do that? Tangent can be written in terms of sine and cosine as what? Tangent is equal to sine over cosine. Okay, so let's start there. So if I have numerator and denominator, and if I want to find the derivative, we have to involve what? Quotient rule. Right, f prime g minus f g prime all over g squared. Oh, that's our goal. We're hoping that after we go through this derivative process, that when everything cleans up, that hopefully we can arrive at the cleaned up version. Okay, so that's our goal. We're just working with that tangent and we want to prove and show that it's equivalent to that secant squared. I'm sorry? Right, we're just doing that to kind of show the relationship, but after we get through this problem, we're not going to want to have to do all this every time. We just want to be able to memorize it and recall it. But yeah, it is basically like a proof. Okay, so we have these rules available. Let's use these here. What's f prime going to be? Okay, sine's derivative is cosine. Original g function, no changes. We drag that down. Back to f. And what's g prime? All over g squared. Cosine times cosine. Cosine squared. Negative sine times negative sine. Positive. Okay, can I do any more cleanup with the numerator? What's cosine squared plus sine squared? Right, Pythagorean identity. Can I represent 1 over cosine squared? Secant squared. There we go. So that's the process that we can do for these other problems. We can basically rewrite everything in terms of sine and cosine and just go through quotient rule and arrive at the derivative. But we're not going to do that. I just want to kind of show that there's that connection between sine and cosine and these other trig function derivatives. Okay. Yes.
Real quick, so how did you, from right there, will you say that again, how you got to 1?
Right, so if we look on the identity sheets, we have a Pythagorean identity that says sine squared plus cosine squared equals 1. So that allows for that to completely clean up. And then once I have 1 over cosine squared, then 1 over cosine is the reciprocal identity is secant squared. Everybody good? So if we were to do this problem, we would start cotangent as cosine over sine and go through quotient rule, and it will clean up much the same way. But in this case, we'll end up with negative cosecant squared. We can rewrite secant as 1 over cosine, either bring it up, go through chain rule, or go through quotient rule. We're going to end up with secant tangent. Cosecant, you can rewrite as 1 over sine, go through chain rule or quotient rule, and arrive at this. But I want to shift our focus and talk about a pattern that I like to use to help us hopefully remember these rules. And I feel like the more patterns that you can see between these functions, these derivatives, the easier hopefully it is to memorize them. So I want to use the space to create that chart, that table for us. So you guys can do this. The nice thing about this pattern is I put sine and cosine next to each other because these are kind of quote unquote the parent functions, and everything's kind of built off of this. Tangent and cotangent have a similar relationship. They're inverses or reciprocals of each other. And then secant and cosecant, typically we consider these as the least used ones, and so I put them next to each other as well. And they're also their derivatives will kind of resemble each other. Okay, so let's fill this out here. I like to use, in terms of u, just as a reminder that there's always that chain rule potential, especially if the u value is more than just an x. So rather than just writing it as cosine of x, let's write it as cosine of u times u prime. So sine of u's derivative is, if we think of it this way, then we're always looking for that potential to involve the inside function's derivative. Okay, cosine's derivative is negative sine of u times u prime. Right, they're kind of similar in the sense that their derivatives kind of involve each other. Okay. Tangent and cotangent, their derivatives will look like each other. And also, I like this pattern here as well, that tangent and secant's derivative are only going to involve each other. And then cotangent and cosecant's derivative will only involve each other as well. So tangent's derivative is secant squared u times u prime. It's just taking the function below it and squaring it. Same thing here, cotangent's derivative is just taking the one below it and squaring it as well, but there's a negative in front. Secant's derivative just involves itself and the one above it. So it's going to be secant u tangent u times u prime. Same pattern here, cosecant is just going to involve itself and the one above it, but there's a negative involved. So if you look, there's a nice relationship here, right? These kind of look similar, or they involve each other. These patterns look like each other. These patterns look like each other. These two functions are just involving each other, and these two derivatives are just involving each other. Okay. Also, the right column, I have it in alphabetical order. They all start with C, COS, COT, CSC. And also something, a nice pattern here as well. What do you notice about all these trig functions that start with C? They all produce what derivative? Negative. That's a nice pattern as well. Right? You know that your negative derivatives will only show up on the right column. You just line up all the C's in alphabetical order. Right? The more patterns that we see, the more connections that we see, the easier it is to memorize these, I feel. So I always tell students, encourage you to put this at the top of the test so you have instant access to 6 derivative rules. On the AP exam, it's even better because if you have this at the top of the AP exam, these only look like it looks like they're only showing 6 rules to you, but it's actually 12 rules because integral rules are just working backwards from them. Okay, so like I don't feel like I really don't memorize the integral rules for trig. I just use my derivative rules and arrive at them. And I feel like, well, there's no need to memorize it if I can just use this and access all 12 rules. Okay, so let's look at example 2. Y equals sine of 5x. We want to find the derivative. This matches nicely with our sine rule. What's our u value? 5x. Okay, so sine of 5x becomes times. Now, are these in the same spots, the 5x and the 5? No, the 5x is inside the trig function. This 5 is outside. We can't merge them and call it 25x. Okay, the best we can do is push that 5 out in front as a coefficient. Yes.
How come at the top of the page it says the derivative of sine is cosine, but we said it's the derivative of sine is cosine times.
Oh, not u squared times u prime.
Oh, u prime.
U prime, yeah.
Sorry.
So technically, this works with the function up top because sine x would become cosine of x times 1. But I like this form better because we can use it to adjust for a wider range of problems because that we're always looking for that u prime. Okay. Okay, back page, page 10. The nice thing about covering trig at the end of the semester is it's a way to kind of review and recap a lot of the first semester material from a trig perspective. But another thing that's nice is that we can work our way to the chain rule for trig. Chain rule for trig is typically the most involving of chain rule. So it's nice that we had this time to kind of get comfortable with chain rule, and then we're able to kind of use that foundation and kind of build on top of it. So typically with chain rule, I always said that we got to identify an outside and inside portion, right? And we take the derivative of each. With trig functions, a lot of times there are a third layer. We got to worry about an outer function's derivative, inside function's derivative, and an inner function's derivative. But the process is the same. We just have to kind of involve that additional layer for our derivative. Okay, so let's explore some of that. Y equals square root of cosine of x squared. Typically, whenever we see a radical, we want to try to rewrite the problem. So how can we rewrite this problem here? Now you may be looking at this going, well, can't some of this cancel out? Can't the squared and the square root cancel out? Typically, yes, if that squared was in the better spot, but that x squared is inside this cosine function, so it's not really accessible with the square root, so it's kind of stuck in that form. Now, I want us to see the different layers that are involved here. You got the outside portion, which is that bracket or parentheses to the 1/2. You got that inside portion, which is the cosine. And then finally, there's that inner portion, which is that x squared. So we're going to have to take turns with each derivative and place them in a different spot away from each other. Okay, so outside derivative first. What's that? Yeah, bracket filled in with the original, right? We don't want to try to find all the derivatives and just make it really compact and clean. It feels nice to do that, but it's not correct, right? We have to really remind ourselves that each derivative is going to be in the separate space, their own space. Okay, so bring down the original function. Okay, so I'm going to check this off. I'm taking care of the outside derivative. I'm moving to a different space. And I'm going to talk about cosine now. What's cosine's derivative? Negative sine, and we're keeping the inside function intact, times the innermost portion, which is 2x. There it is. 3 different derivatives, each with their own space, each, in a sense, kind of chained together. Oh yeah, I forgot to do that, sorry. So I brought the 1/2 down, but I need to finish power rule. 1/2 minus 1 is -1/2. Outside derivative, inside derivative, innermost portions derivative. Now, I do want to point something out here. I like to do it in this form to kind of make sure that we see the different layers. But at the same time, if you think of this layer as within the derivative rule for cosine, then you don't have to do that. So what I mean is this. If you just follow this rule to its end, negative sine of u times u prime, then that 2x is just going to take care of itself. So I don't want you to think that, oh, I got to do this 2x and I got to do this inner. So this is kind of a duplicate. So either you feel like you want to go through this process or you want to just go through the chain rule within cosine. Either way, just have to make sure that the 2x shows up. All right. So there's our derivative. We can do a little bit of cleanup. All this is being multiplied, so we kind of rearrange and cancel out and reduce if we can. The 2's can cancel out. One's in the numerator, one's in the denominator. And now I'm just going to push these together here. These belong in the numerator, and I can push that cosine square down to the denominator. Okay, let's try example 4 as well. Very similar process. Rewrite that radical as a rational exponent. Okay, outside derivative, let's take care of that power rule. Everybody good so far? Outside derivative. We can check that off. Move on to the next function. It's going to be in its own space. We don't want to put it all into one space, right? So they're all going to be in a different space. Tangent's derivative is so either you can think of it as secant squared u times u prime, or take that inner function derivative. Times, what's the last part? Okay, that's a messy derivative. I'm going to see if I can clean this up a little bit here. I actually can think of this as GCF I can factor out of 3, and then that 3 can handle match with that 3. So if I think of 24x cubed plus 3 as 3 factored out being 8x cubed plus 1, then I can remove the 3 in the numerator and denominator. I know they're really far apart, but they're all being multiplied and divided, so I can just reach across and see what can reduce. So here's my merging process here. I can put the numerators together, and I can push this tangent down to the denominator because of the negative exponent. The order of the numerator doesn't matter. Okay, any questions before? Okay, no questions here. Example 5, we're just going to find y prime. I know it says y double prime, but y double prime is a little bit too much for us right now. We're just going to find y prime. But I do want you to put a star next to it. This type of a setup is not necessarily difficult, but it can be, it can cause issues if we're not careful. Okay. So what I mean is, I think the cost of us not seeing what needs to be done is that squared. That squared is written in a shorthand form. This is typically how they write an expression if they want to square or raise a trig function to a power. They put it there. Because if they put it outside, they would have to put another set of bracket or parentheses. And this is kind of a shorthand way of doing it. But for our purposes, because we're trying to find a derivative, we have to recognize the need for chain rule. Visually, it's going to be a lot more helpful if we can write that squared or that exponent in a more visually helpful location. So typically what I see is when students don't take the additional step to rewrite it, that's typically when I see students miss out on the chain rule, and typically they miss that problem because visually they're not seeing it. Right? So if you don't do it, doesn't mean that I'll take points off. If you get the right answer, that's fine, but just want to kind of show you the pattern that I've seen over the years, and it's a lot more helpful that this can be written in a better way. So let's rewrite this. Y is equal to that squared is really belonging outside the trig function. So if you can just take that additional step, then it becomes a problem that's like example 3 and 4. And you can move through the process a lot easier. You can identify your outside, inside, inner portion a lot clearer. And I think that can help us avoid potential mistakes. So see if you can go through this. Identify your outside, inside, and inner. And step through chain rule each derivative process. outside derivative, 2 bracket to the first power, or 2 parentheses to the first power, right? Just power rule here. Check that off. We took care of that derivative. What's secant derivative? Yeah, secant u, tangent u, and we can replace the u with what we see here, right? If you want to think of it as times u prime, that's fine. Or you can look at this and find this derivative. Either way, you're just going to do it once, times plus pi x's derivative. Okay, here. We'll do a little bit of cleanup. I'm going to push the 2 and the pi together as coefficient. I'm going to merge the secants together. Questions with 5?
Can we put that in like
That's fine. Yeah, that's fine. All right, example 6. Anything that you notice here with 6? Any process that's involved here based off of how this is set up? Implicit, right? You see y's all over the place. Is there anything that we can do with that sign of x plus y? Yes, question? Yeah, sure. Oh, from the second, from this. Okay. So everything is being multiplied, so I can just rearrange everything in whatever order I want. So I just put the 2 and the pi in front. And the secant pi x, secant pi, these are like terms. If I just multiply them together, I can just make this secant pi x squared, which the shorthand way is writing it in that form, secant squared pi x. Okay. So example 6, you guys said implicit. We got to deal with that. Is there anything that I can do with that sign of x plus y? Okay, so that's what I want to talk about, is that, yes, there is some identity that we can use, but we're not going to worry about those identity from pre-calc. But I do want to point out that, can we distribute the sign through the parentheses? So we can't do that. Because the x plus y, the sign is not outside the function. It's not a separate entity. So I want to kind of show you this instance here. If I had sine x times x plus y, then yes, I can distribute through. But when I have sine of x plus y, the x plus y is inside the sign. The sign is not a standalone, so I can't distribute the sign through. Does that make sense? Yeah, this sign is not a standalone. Unless it's sine x, then that's a standalone. Then I can distribute that through. But this is kind of stuck. Okay, so I wanted to think of the fact that that's basically our u value, and we can jump into the derivative that way. Okay, so let's explore the derivative for sine of x plus y. Sine of x plus y becomes what? Good. So we took care of cosine of u. When we reach u prime means I got to take the full derivative of everything I see inside the parentheses. I explored one term at a time. X becomes 1, and then y becomes dy dx. Over on the right side, 3x becomes, and then 2y becomes So that ends the derivative process. The rest of it is just trying to clean up. I want to point something out here. What's the difference between this parentheses and this parentheses? Say it again. Okay. Right. So this is inside the cosine, but this is outside. Okay. So this is a package deal here. We can't do anything to separate it, but I can distribute this through the parentheses to help separate that dy dx from its parentheses. Okay. So we'll finish this problem tomorrow. You guys have homework from Trig Derivatives. I'll be checking it on Thursday. Tomorrow is Senior Service Day. You guys, the non-seniors will be, if you're here at school, non-seniors will report to Mr. Goodell's room. I'll also post it on my door, and this would be a study hall day for you in my class. Okay, all right, I'll fix that. Okay, appreciate it. Yeah, I'll fix this. Thank you.